Write it down. As long as I don't forget.
So we're fortunate today to have Bob Spero from JPL to talk to us about LISA lasers and optics. Bob got his PhD with Riley Newman at the University of California at Irvine, I guess around 1980.
That's right.
And then he came here immediately thereafter, joining the brand new effort in gravitational wave detection that Ron Drever was just starting at that time. So Bob was a mainstay in the gravitational wave effort here on campus for something like 15 years, I would say, until he moved up to JPL as one of the key scientists, initially on the SIM project and now on LISA. And so Bob probably knows more than almost anybody else about in the world about the optics issues and a lot of other issues connected both to LIGO and LISA.
Thanks. Moved up to JPL, I suppose, in more than one sense. The view graphs for this lecture are available on the web. And I thought I'd start by trotting out this comparison between LISA and LIGO that people have probably seen. They've got apparent similarities. They both have this U-shaped curve. They have similar sensitivities, at least as plotted here. There are some important differences. The LISA is the first LISA, and the LIGO curve here is a more advanced LIGO, both off in the future some. I suppose you could say that although they're both pie in the sky, only one of them is literally pies in the sky. Just for the fun of it, I drew this green line, which is the acceleration sensitivity of LIGO. If it had the same acceleration sensitivity it has at 100 hertz down at low frequencies, you can see it's a couple of orders of magnitude above that of LISA, and this is just to add to the list of experiments you heard from Bill Faulkner on Monday about various experiments with different acceleration sensitivities.
So let me understand, that's if you were to have LIGO test mass accelerations with a LISA arm length?
That's right. And if so, right. So yeah, if we just were to take the LIGO arm length, we would take this point and extrapolate it up as f squared, but we get to bring it down by several orders of magnitude by the ratio of 5 million kilometers to 40 meters. Another feature that characterizes the detectors and is useful in looking at comparisons is the frequency that corresponds to an arm length, that is C over L. Because for signals that are lower in frequency than that length, shown as the vertical red line here, the detector is operating in the long wave limit. That is, the wavelength of the signal is large compared to the separation between the proof masses. And above that's the short wave limit. LISA, probably not surprisingly, or for good reason, sort of straddles both regimes. And that's just the nature of a single bounce Michelson interferometer, that the best sensitivity is going to be at the frequency that corresponds to the light travel time or the light storage time, which is the same as the one-way travel time. LIGO, by contrast, uses this trick of building up the storage time, so having a storage time that's longer than the one-way travel time, and as a result, it operates exclusively in the long wave limit. There's a couple of ways you can think about the difference between a long wave limit and a short wave limit detector. For example, in the long wave limit, it's convenient to pick a metric, or just to think of the effect of the wave as operating on the masses, this local Lorentz invariant frame. Well, probably in the short wave limit, it's more natural to think of the wave as affecting the beam of light and the masses as being in free fall. A more practical distinction might be the effect of frequency noise. If you're in the long wave limit, such as these frequencies, 10 to the minus 4, 10 to the minus 5 hertz for LISA, the fact that the propagation time from, or the round trip time from the central mass out to the end and back again is short compared to the signal gives you the opportunity to use the same kind of control systems, relatively high bandwidth, that's relative to the signal frequency, controls that are used on LIGO and other ground-based detectors for stabilizing the frequency of the laser. On the other hand, in the shortwave limit on LISA, you can exploit the delay, as we'll hear from John Armstrong next, by using it to effectively measure the frequency noise of the laser. If you've got a measurement of the phase at one time and another time that's delayed, that's a way of getting a handle on it. And there are various algorithms and even control system methods for suppressing it once you have that information. And both of these techniques, of course, can span either side of that red line. And that's just a matter of optimization, which is best. For the rest of this talk, we'll be discussing, we'll sort of look under the hood of LISA. Not quite at the detailed level you saw Monday, where you see very impressive layouts with dozens of quarter wave plates and mysterious widgets, because LISA isn't going to launch for a dozen years, and let's face it, that level of detail is going to change many times over between now and launch. But rather what I'd like to get across is the concepts behind things at a level that aren't likely to change, and also from those concepts try to make the connection to, as quantitatively as makes sense, try to make the connection to the performance. So this is going to be a bit more in the style of a traditional lecture, and I actually don't have enough material for 90 minutes, so I encourage people to interrupt me with questions along the way. So one characteristic of LISA, of the beams that traverse between the spacecraft on LISA, is that with the standard parameters of 30 centimeter diameter mirrors and 5 million kilometer separation, optically we're in the far field limit. That is, it's a good approximation to say that the beam is diverging linearly with the separation between the spacecraft. And that's just this Gaussian beam approximation here. The beam size is proportional to z, the distance, with this proportionality constant 1 over the Rayleigh range, where W naught is the radius of the beam. This harkens back to one of the first lectures given by Kip, so you've seen this before. And typically you'll adjust the size of the mirror to be about twice the waist size, just to make sure you catch almost all the light. So sticking in the numbers that we know for LISA, 1 micron wavelength, 30 centimeter diameter mirror, 5 million kilometer separation, that divergence angle works out to be about 2 microradians. The Rayleigh range, 67 kilometers, that characterizes the region that the beam is relatively constant, sort of the longitudinal dimension of the waist, if you like, before it starts diverging. So the fact that that's shorter than 5 million kilometers is another way of saying that we're in the far field limit. By the time the beam gets out to the distant spacecraft, it's grown to 11 kilometers in radius, and therefore it's attenuated by this factor of 2 times 10 to the minus 10, which is the size of the telescope divided by the size of the beam squared. So that means if you start out with a watt, you've just got hundreds of picowatts detected. And if we were to stick a mirror there, do the simple-minded thing that you do on the ground-based detectors, you get that same attenuation factor on the way back. So after a round trip, if you start out with a watt, you'll end up with less than a photon per second, which is something, but it's not enough to split the fringe as finely as LISA requires. So it wouldn't be a very sensitive gravity wave detector if we just put mirrors to reflect the light back.
But it's worth emphasizing that's how laser ranging to the moon works.
That's true. They get less than a photon per second, actually.
And still they're able to monitor the Earth-Moon distance.
Right. They don't split fringes, though.
No,
They get multi-fringe resolution, I think.
well, they get accuracies of order of centimeter.
Right. Of course, it's non-interferometric. So.
You're doing, of course, much less.
Right. But also, it's just for entertainment. One can ask, how big would the mirrors have to be to catch all the light on LISA-style baselines? Because once you do that, it's qualitatively different. Then you can imagine using the same sort of techniques that are used on the ground with optical resonators and all the various topologies that have been and are being developed for ground-based detectors. Well, if the telescope mirror is very large, there won't be any divergence at all. That is, the two spacecraft will be within the Rayleigh range defined by that mirror diameter, and that's, you can see that's this line approaching that asymptote of the detected beam being the same size. Here's the size of the launch beam. Here's the size of the detected beam. And being equal size, when you get a very large mirror, on the other hand, it's impracticably large. If the Rayleigh range is equal to the separation, then you get a minimum in the size of the detected beam. And if the then when we get down to more practically sized mirrors, then you can see that the detected beam gets much bigger. In fact, this is in meters, so the real thing is off scale here. So the answer is a mirror diameter of 116 meters would be required on the 5 million kilometer baseline. If, on the other hand, you were to consider a shorter LISA, maybe it makes sense to use a Hubble-type mirror. Maybe it's conceivable, at least. I'm not proposing it. And catch all the light. That would be still thousands of kilometers. So returning to the detectability of the light, the one-way detected power is 100 picowatts. Now, can you pick that up if you just had a photodetector? And, well, the question really is the noise in that photodetector above or below shot noise in that 100 picowatts? So the first computation then is to compute the spectrum of shot noise from a 100-watt beam. It's the square root of 2 times that DC power times h nu, which is 6 times 10 minus 15 watts per root hertz. And the next piece is to compare that with what the noise level of detectors is. And there's great interest in making detectors that are very quiet, primarily for communications purposes. It's a matter of reducing semiconductor noise and optimizing circuitry, and sort of companies in the business of doing just that. And this plot is a scatter plot, these triangles, the actual models you can buy of detector amplifier combinations, plotted as a function of the bandwidth of the detector, what the noise equivalent power of that detector is. So the noise equivalent power is the minimum power that can be detected in the bandwidth of 1 hertz. It's the signal to noise ratio equals 1 detectable power in 1 hertz bandwidth. Now the bandwidth here means it's not the signal bandwidth like on these sensitivity plots we saw, but it's the speed with which the detector can respond to changes in the amplitude of the signal, the intensity of the signal. You might say LISA doesn't need much bandwidth, but it probably does, at least under most schemes we're considering, because of the Doppler shift. The spacecraft, as you heard Monday, are moving at relative velocities of several meters per second, and at our wavelength, 1 micron, each meter per second gives 1 megahertz of Doppler shift. So we might need something on the order of a megahertz bandwidth. And you can see the NEPs for these high-quality communication sort of optimized detectors are well above the required NEP level of 6 times 10 to the minus 15 watts per hertz. They're more like 10 to the minus 12 watts per hertz. So that doesn't work. But there is something that can be done to overcome this problem of electronic noise. And that's an extension of a time-honored technique from radio and microwave electronics that applied to the optical, and that's to beat the very weak incoming signal beam against the strong local laser called the local oscillator, combine them on a beam splitter, mix them on a photodetector. The photodetector is an amplitude device, so it sees the square of the sum of the fields, and the relevant piece of that is the cross term, which contains the phase information. This is something I'm showing just sort of to connect with probably what you've seen before, the technique of phase modulating the light to tag it, so the photodiode doesn't have to operate at DC, and then demodulating and feeding back to the laser so that the intensity on the photodiode is always dark. It's sort of convenient, but it's also necessary in any practical situation where the laser has a lot of low frequency variation in its amplitude. And I won't bother you with the sideband expansion because you've seen that before.
Okay, so you put modulation on the frequency of a little omega. And what frequency do you modulate at?
You typically will pick a frequency where there isn't other noise. So if you've got a fairly quiet laser, that can be a megahertz or below, maybe tens of kilohertz. And also you don't want to make it too high in frequency that it exceeds the bandwidth of the detector. So if you can actually buy these offset locking electronics commercially. The same company that sells the lasers sell boxes that you can plug together, and out comes, in comes one laser beam and out comes another laser beam that's shifted by, say, typically 10 megahertz. Which brings us to the transponder topic. We don't need only to detect the light at the distant spacecraft. We need to relay it back. So there's a weak beam coming in, and we want to send a strong beam out that contains the phase information on the weak beam. And you could imagine doing that in the simplest case by adjusting the frequency of the laser to always keep the combined intensity on the photodetector constant. That's a so-called DC lock. Again, it's not going to be very precise because this old problem of 1 over F noise in the intensity of the light and the photodetection electronics would be imposed upon the beam. So that would be a noisy transponder. It's undesirable. But in a slight variation on the frequency offset locking you saw before, this is a little closer to what I think people are usually considering for the LISA transponder, in which the weak beam comes in, and again it's mixed with a strong local oscillator beam. This time there's a sine wave added or multiplied in this mixer with the detected beam. The effect of that is to frequency shift the signal from DC up to, say, 10 megahertz. And this control system imposes that frequency on the laser. So now this beam is, say, 10 megahertz higher than this beam, but it's still phase locked because this very high gain control system, the feedback to the laser, drives the signal here to be dark. Is that clear?
Sort of. It's obviously clear to everybody else.
Maybe it would help to say what the frequency is of the beam at various places. Okay. So, well, first of all, let's discuss it first, open loop. Open loop, you'd have some signal come in here.
That's coming in
from the distant spacecraft, right? And it may or may not, it'll have some Doppler shift on it relative to this spacecraft because they're moving relative to each other. Say it's a megahertz Doppler shift. So let's say that, and let's say this was a perfect laser, and the same as the launch laser. So the frequency of the incoming beam now is a megahertz higher than the beam that comes out of the laser. So this photodetector would see, because of Doppler shift. So this photodetector would see a 1 megahertz sinusoid. Now let's just imagine that this oscillator, it's just a sine wave, electronic sine wave generator on the spacecraft, is tuned to exactly 1 megahertz. The effect, what this mixer does in multiplying those two is shift the incoming 1 megahertz by this frequency, shifts it down. So out of the mixer is 0 megahertz, but 0 amplitude at the frequencies of interest. So
these are all sidebands on your carrier, which is up at
3 times 10 to the 14 hertz, right? That's right. So there's nothing that comes out of here, no correction applied to the laser, and we have a stable situation right now where this laser is outputting a signal that's 1 megahertz different from the input signal. Now, if the frequency of this input signal changes, so the Doppler shift is no longer 1 megahertz because, say, the relative spacecraft velocities change, then the output here will have some component at that difference frequency. Let's say this is 2 megahertz compared to the 1 megahertz. So there's now, this amplifier sees a 1 megahertz sinusoidal voltage. That gets applied with high gain to the laser, causing the laser frequency now to oscillate at 1 megahertz. So the effect is there's still a 1 megahertz, probably I picked bad numbers for the case of this example, but there's now a shift. I think it's probably a 2 megahertz shift if I keep all the numbers straight. This laser is now 1 megahertz different from the launch laser down below. So that's the sense that it's offset. Well, it's also offset compared to the input beam by that 1 megahertz. Now, there's a problem. There's a technical problem, but a very
So the goal is to guarantee that the signal going out it really does have the same frequency as the signal that came in.
Not necessarily. I mean, the offset is, there's no fundamental reason that the offset is intolerable. Like I say, it's nice to have.
You know what it is.
I think if it's fixed.
Okay.
The concern is, the only concern with this scheme is a technical one, but it seems to be a serious technical one. And that's that if this is not a perfect oscillator, it's going to impose noise on this output beam. So
that little generator, that's acting like the local oscillator?
Yes, although we should probably try to keep the terminology straight. This is an optical local oscillator, so the photodiode does mixing. It's a nonlinear device because it converts the amplitudes to intensities. This is an electronic mixer. This is a mixer working up at 3 times 10 to 14 hertz. This mixer works around a megahertz. But yeah, it's the same principle in both cases. So as I said, the concern about this is that if the phase of this sky is wandering around a little bit, it's going to be indistinguishable from, say, motion of the spacecraft, because that frequency is like the Doppler, change in the Doppler frequency. And that's going to look like gravity wave noise. And just, maybe it will help, just occurred to me to set the scale of what's going on, the various signal amplitudes and time scales for LISA. The separation of the spacecraft, as you saw yesterday in the orbits, is varying sinusoidally. You sort of take the worst case with a period of 1 year. And the amplitude of this variation is just this change in the separation of the spacecraft, which is that right, Bonnie? About 100,000 kilometers? I think it's typically about 1% of the distance between the spacecraft.
The 1% is the difference in the outlines between two different outlines.
Okay, well, maybe that's coincidental, but if you look at the pictures of the orbits, I think the separation between spacecraft are changing over an annual period by about this much. Is that right?
Well, it's 10 meters per second is the sinusoid, so you can integrate that.
Right. I think this is what you get, but maybe we'll leave that as an exercise for the student. Anyway, the point is these spacecraft are in real orbits. There are large macroscopic motions of the spacecraft for this annual period. And what we're looking for, let's say we were looking for a millihertz burst. A year is 3 times 10 to the 7 seconds. So we want a 10,000th of that in time, say for a or maybe a 1,000th of that for a 10 to the minus 4 hertz burst. We want to see a little roughness in this curve. How little? Well, integrated over the whole duration of it, I think about 10 to the minus 13 meters. So you can see a huge range. And one way of thinking of the operation of LISA is we are just recording this signal, the smooth signal and whatever gravity wave might be on top of that, by recording the phase of this incoming light after doing all the corrections for noise of various frequency noise and lasers and things like that. So it looks next to impossible. This is 10 to the 8th meters. This is 10 to the minus 13 meters. A ratio of 10 to the 21. But what we rely on is the smoothness of this sine wave. That is, if you think of the orbital motion of the planets or of the spacecraft as a mechanical oscillator, it's an extremely high Q mechanical oscillator. So if we were to plot this in the frequency space, way down here at 1 per year, and this is, say, the square root of the PSD of delta x, separation between spacecraft, there indeed will be a many orders of magnitude high peak at that period, but by the time we've moved off the 3 decades or so to where the signal is, that very sharp peak will have no contribution to the noise. One thing it does put a constraint on is that if we were just to keep track of the phase, is you need a lot of bits in your computer to make sure that you don't overflow. Okay. So as I said, the undesirability of the standard offset locking is that phase noise in the oscillator is imposed on the transponded beam. So a few of us, including Bonnie, got together last week to discuss what might be done about that. And Daniel Shattuck mentioned, the postdoc at JPL mentioned this idea that, well, you can just take the frequency out of the light that is the same, and so now it's no longer offset. This box here is an Acousto-Optic Modulator. It's a commercially available device. There's one in every laser printer that works by generating acoustic waves in a piece of glass, and as the light comes in, the scattering between the phonons from that acoustic wave and the photons in the light cause a frequency shift in the output beam, where that frequency shift is equal to whatever signal is put in. And there's also an unshifted beam. So this, you can think of this as a live diffraction grating as far as the deflection goes. So the idea is that now it's just like this scheme up here, but now that the frequency difference that would normally be applied, normally generating the offset here, is reapplied to the light, so that there is no frequency difference. And so what? It's nice that the input and output beam have the same frequency, but the real beauty of this is that because there's no frequency difference, it is insensitive to the frequency of this oscillator, and therefore also insensitive to the noise in that oscillator. Now, the innovation that Daniel Shattuck came up with was, well, the concern is that as soon as you stick this piece of glass in there, you've introduced thermal sensitivity. And in fact, as the expansion of that glass, as the temperature of that glass changes, it's not particularly low expansion coefficient material. It'll change its optical path, and that would be indistinguishable from a gravity wave. So the innovation is this trick of using the undeflected, unshifted beam plus the deflected frequency shifted beam to subtract out, to suppress the effect of any thermal changes. That is, both beams see the same thermal change, and therefore it doesn't appear in the output signal. So let's run with that transponder idea. For the time, leaving it unspecified, the details of how the transponding works, but let's just let's say that we start with a laser here, send it out in two directions. This laser will be slaved in the sense that it's locked to the input beam. So and let's assume that this is the offset-free transponding. There's no phase difference, no frequency difference between the return beam and the input beam. That's what that 0 signifies. And similarly, for the other arm of that first interferometer, this laser is locked to this input beam. So these are like mirrors. We have two signals coming back, two phase measurements. You can get the gravity wave information by subtracting the two. But we've got another degree of freedom left over, which is the average of the two, or just one of them. And that can be used to measure, subtract, or perhaps suppress in a control system the frequency noise, because that sum is sensitive to frequency fluctuations in the laser. Oh, and similarly, same idea works for the other arm. So that I just went through this arm 1, 2 versus 1, 3, and you subtract the phases. 1, 2, 2, 3 is the same, and for the last one, 2, 3, 1, 3. So that's this interferometer. There's nothing to subtract there, but we do have a measure of the difference in the frequencies of the two lasers. So that the availability of that signal is, for that arm allows us to subtract away the frequency noise there.
So you've got two lasers on one of your spacecraft and only one on
Yeah, no,
is that really the way you planned it?
no, this is conceptual, but it's easy enough to have two lasers locked together, and then it's equivalent.
And so, how do you plan to operate? I mean, in this particular scheme, you have some master oscillator sitting at that left hand
Right.
or left.
This would be stabilized to some reference cavity.
And so, do you intend to operate with one master oscillator like that, or?
That's right. In fact, this is, as far as I can tell, reading between the lines, this is the baseline plan, at least up until very recently, up until the time delay interferometry ideas caught on. This is, and I think it's still favored by the people in Glasgow. I'm not sure. Is that right, Bonnie? No.
I can't speak for them.
Okay. But it's
It's not exactly what it was.
okay. But the baseline plan is this pretty much this transponder idea, and to have this asymmetry of one reference cavity, one master laser. Is that right, Massimo?
Yeah, but you haven't talked about what the fluctuations introduced by the transponding process itself are on the returning beam.
Well, I thought I did.
The scheme we are talking about assumes that the fluctuation of the laser, the master laser, going to the end and then come back exactly the same. Well, you have other lasers at the end which will have to follow the incoming frequency of the incoming beams, but not only those, they have to follow also the fluctuations of the light coming to them at the same level, down to passing 10⁻². And what we have been talking on was only DC frequencies, not the fluctuations on those frequencies.
The fluctuations in the transponding process itself, you mean?
Well, yeah, I mean, you have another laser that's sending back has to reflect exactly the same fluctuations that you receive.
And that's what Rocky Road F, he meant that they were phase locked, that's frequency locked.
But the fluctuations also. So they act like exactly like mirrors. It's not just the frequency that comes back, but also the fluctuations.
If
of
it's
the
phase
laser.
locked at every moment, then all the phase fluctuations will also be following.
Actually, there are a lot of details in how the noise is propagated through the system that I'm not going to talk about, but I'm hoping John will in his talk. Okay, so let's talk a little bit more about the effect of laser frequency noise. And for convenience, I'm looking at this in the long wave limit. The short wave limit is the one that you might think of more naturally if you use the spacecraft tracking, but you can always transition across that wavelength boundary, either concept. So this is the same analysis, because it's a long wave limit, that you see in the ground-based detectors. It's the same analysis of the effect of frequency noise. That is the signal is just the difference, the change in the length difference divided by the length, which is just the change in the phase, this measured phase that we talked about. The requirement is 10⁻21 per root hertz. That's to be compared with the effect of laser frequency noise on an arm length mismatch that's about 1% of the arm length. That is, S is the mismatch, L is the arm length. So there's a sort of a suppression of laser frequency noise by the fact that the arms are matched to within 1%. And the delta F over F, not part of that. Delta F is expected to be on the order of 30 hertz per root hertz. That is, we take one of these lasers oscillating at 3 × 10⁻14 hertz, stabilize it to a reference cavity that has a temperature variation of only a microkelvin per root hertz, and we think the temperature is perhaps the only thing that's changing the frequency of that reference cavity. And the stabilized light is varying at 30 hertz per root hertz, which corresponds to a strain sensitivity of 10⁻15 per root hertz.
Sorry, which is those should be per root hertz.
Those should be per root hertz. Thank you. That is, as you can see, 6 orders of magnitude above the requirement, so it would be an intolerable background noise. We need some way of suppressing it. And one way, as I alluded to, is to measure it in that redundant signal, the phi12 from the previous plot. Just a single arm, the sum of the two arms. So we'll get it right. And another way would be to not just measure it and subtract it, but to feed it back, all ground-based detectors. That is, this is something that's done in LIGO type or prototype detectors, is that frequency error from looking at one of the arms is fed back to the laser to suppress it. Well, there's a catch, there's a limitation to how accurately that suppression can be done on LISA, and that's because of the delay. And this is where the long wavelength approximation breaks down. So the challenge is a control system problem. And it's perhaps the control system problem, or the prototypical control system problem. And that's to have a control system that works around a delay. So what I mean is, you have a laser that needs to be stabilized. You've got some phase relative to some input beam. Call it a phase meter. You have a delay. T naught. And you have some kind of phase correction electronics. And the question is, at a given frequency of fluctuation, of disturbance that needs to be corrected, and in the presence of this delay, what is the accuracy with which that correction can be made? Maybe, have people covered control systems in previous talks? Okay, so this is probably familiar ground then. The delay for the two-way transit is 60 seconds, which is right around here, a few 10 to the minus 2 hertz. The sort of rule of thumb is that and it's more than that, it's a fundamental causality consideration, is that it's not allowed to have any correction, any gain, at that frequency, otherwise the control system would be unstable. And control system theory also tells us how quickly we can add gain as we go down in frequency, and I just kind of arbitrarily sketched a controller that has a roll-off of f to the minus 1.5 for 2 decades and then f to the minus 2. So we can see that, say at 10 to the minus 4 hertz, you've got a respectable gain of about 1,000. Still not enough, but by the time you get down to 10 to the 5 hertz, it's perhaps enough. But at a millihertz, it's only a gain of 50, so it's inadequate. So this technique alone doesn't work.
This is the issue that we saw in an earlier lecture and in the homework. You put in a phase delay, and if you don't do appropriate filtering, then your servo loop is going to be unstable. We look at that instability.
Right.
And we look at suppressing on a problem center.
Can I choose the pick? We need to close that sentence.
So it's time for some jokes. Anybody have any good jokes?
It's your job.